Okay, hello, today we're going to be solving exercise 2.5. We have to verify that this inner product that we just defined in the textbook is an inner product on an n-dimensional complex number, plural. So recall that the definition of this function that we just made is this thing, is the sum of the conjugate of yi times zi. And in order to prove that it's an inner product, we have to prove the three properties of linearity in the second argument, us being able to flip the arguments and that being equal to the conjugate, and then also it has to be always greater than or equal to 0 when we use the function on the same argument twice. So we'll start with the first one, linearity. And in order to prove this, we will basically start out with a linear expression here. So here I'll say j. So each of these zj's has a coefficient, and we want to prove that this is linear so that we can take the sum and the coefficients out. So the way we'll do this is first we'll just use the definition. So we got yi conjugate, and then times, just the second argument. Yeah, basically just that. And from here, we'll just simply switch around the sums. So we can go take the lambda out, and then switching around the sums lets us put this yi in the inside. And yeah, this is allowed because of the rules of sums. And from here, well, notice this thing right here is literally just the definition of the inner product. So now we have an inner product of y and zj, and bang, there's our linearity condition. Now for the second condition, we have to prove that we can switch the arguments and it's equal to the conjugate. So again, we'll start out with a y and z and use the definition here, and then we'll just manipulate it a little bit. So I'll say yi and zi. Okay, now we'll kind of factor out a conjugate. And what I mean by that is if we take the conjugate of both and put it on the outside, see, this will distribute inside and it'll just become equal. So these last two are the same thing. And because of the laws of the conjugate, we can just take this, we can put the sum inside as well, because addition doesn't change the fact that it's the conjugate. So we can have like this. And I just switched around the arguments. So put this as an I, switch around the arguments, and put the conjugate on the very outside. And now you'll notice this is the same thing as z comma y conjugate. And this is our second property. We can switch around the arguments and it's equal to the conjugate. Okay, third property, we want to say that we take the inner product of the same vector. It has to be greater than or equal to 0 with equality if and only if that vector is equal to 0. So we'll just expand this a little bit. Using the definition, we have this thing. And notice this is literally just the magnitude of yi, the complex number yi, the squared magnitude. So I'm just going to write it that way. And the squared magnitude, another way to write that in terms of the real and imaginary parts, is just using Pythagorean theorem. It's the real part squared plus the imaginary part squared. So these are equal. And you'll notice the real part squared, this is a real number. and the real part is just a real number, and having a real number squared must be greater than or equal to 0. And the imaginary part is also a real number because it's the imaginary part. It's not, doesn't have the I on it. And squaring that also must be greater than or equal to 0. Therefore, we have that this thing must be greater than or equal to 0. And in order for it to be 0, well, look at this. I'll use this highlighter. Look at this sum right here. It's going to have a bunch of terms, and since none of them are allowed to be negative, they all must be 0 in order for this whole thing to be 0. And for each of these terms to be 0, the real part and imaginary part of each element in the vector must also be 0. Therefore, y must equal 0. Or I'll say, yeah, if and only if, just a biconditional, it's equal to 0. Okay, and that's our third property. Therefore, we have that this function is an inner product on Cn. Thank you.